Today I will go over k nearest neighbor method, and in fact this method a lot of people confuse with k means clustering. So please note that here we can do supervised learning for both classification and regression, whereas k means clustering is mostly non-supervised method. Let's ask Google what is a k nearest neighbor. Okay Google, what is k nearest neighbor?
According to Wikipedia, in pattern recognition, the k-nearest neighbors algorithm is a non-parametric method used for classification and regression.
So in fact, in this session, we'll go over both examples, one example for classification and another example for regression. Let me use a small example where we are looking at students applying to a graduate program, and two important things are GRE scores and GPA. So if you do a scatter plot of GRE score and GPA, this is a made up example. So let's say our scatter plot looks like this. So where circles indicate a student application was not accepted and cross indicates that the student application was accepted. Now let's consider a point to be a new application. So what we do in k nearest neighbor is we look at a few nearest neighbors, in fact k nearest neighbors, and see what is the situation there before we make a prediction about the new data point. So if you consider k to be 3, which means we look at the 3 closest neighbors to this new data point, you find that in 2 cases student applications were rejected, and in 1 case student application was accepted. So because the majority vote is towards not accepting the candidate, so the prediction will be that we classify this new application towards not accepting. But if we increase our k to 5, in that case you can see 3 applicants in the past were accepted and 2 were rejected. So that would lead to a conclusion where we accept this new application. So I have kept k as an odd number just to make sure that we don't end up with ties. If we are doing regression, so instead of voting, we look at the mean of 3 numbers or 5 numbers or whatever our k is. Now, one important thing is how we find out how far or close a data point is from the neighbors. And for that, we make use of distance measure. And most commonly used method is Euclidean method. As you may know, Euclid was Greek mathematician who came up with this process of finding distance between 2 points. So if we consider a two-dimensional case, and if our data points are P and Q, then we can calculate distance as square root of Q1 minus P1 whole square plus Q2 minus P2 whole square. So this is exactly what is done in Pythagoras theorem, where we have 2 points P and Q, and we make use of the length of the two sides, and using that we calculate the distance between P and Q. If you extend this to three-dimensional situation, then our formula looks like this. And then if you want to create a general formula, we have square root of total of Pi minus Qi whole square. Another way we calculate distance is called Manhattan method. What we do there is we take the total of absolute value of difference between Pi and Qi. And another method is Minkowski method, and Euclidean distance is the most commonly used one, and in this session we'll make use of that. Another important thing to remember is because we may be dealing with various variables that may have totally different magnitudes. For example, GRE scores may be in hundreds like 300, 400 and so on, whereas the GPA scores could be just maybe 2.5 or 3.5. So it is very important to standardize those kind of variables so that we create a level playing field for all the variables that we have in our data set. One most commonly used method for standardization is normalizing the data or calculating z-score. From each value, we subtract mean and divide by standard deviation. And the value of this z-score lies between -3 and +3. Another popular method is minimax, where From each data point, we subtract maximum value and then divide it by maximum minus minimum. So basically range of the data set, and that creates a new range which varies from 0 to 1. So these two are very commonly used methods. In this session, we'll use the first one. Now coming to some popular application examples of applying k-nearest neighbor method. It has been used in recommendation systems, anomaly detection, text categorization, finance, and medicine. So next we see how do we apply k-nearest neighbor method to classification as well as regression. So we read this data file that has 400 observations with 4 variables. Let's look at the structure. So this is data on student applications where we have information about whether a student was admitted, GRE values, GPA, and rank of the school from where these students applied. First of all, I want to use this admit variable as a factor variable. So whether a student was admitted or not. Let me make some changes. Instead of 0 and 1, I'm going to say, so when admit value is equal to 0, so let's replace 0 by no, meaning that student was not admitted. Similarly, when the value is 1, let's say yes, that the student was admitted. So if you run structured data again, you'll see that admit is a character variable which has values like no and yes. So I'm going to change admit to a factor variable by using factor data $admit. So now if you look at structure of data again, you can see admit is a factor variable. Let's start by using set.seed 1, 2, 3, 4 so that we get same training and test data. So I'm going to take independent sample of size 2. N row, number of row is whatever we have in data. This is a sampling with replacement and the probability that we want. So let's say training data is about 70% and test data about 30%. So within training we can save those rows in the data where I and D equals 2 equal signs and 1. And after comma nothing means all columns are included. So in the training data we get 284 observations out of 400. So test data has remaining 116 observations. Before we make a k-nearest neighbor model, let's specify train control. So we'll call it tr control and we are going to use function train control from correct package. For developing the model, we'll use a method which is called repeated CV or repeated cross validation. And for number of resampling iterations, let's use 10, and repeats, which is a number of complete set of folds to repeat this cross validation. So let's use 3. So we'll repeat the whole thing 3 times. Now before we fit the model, let's use set.seed so that we have repeatability of the outcome. Let's use 2, 2, 2. Let's save fitted model in fit and we are going to use train function. So our response variable is admit. We are creating a model with admit versus all the independent variables which are GRE, GPA and rank. For all the variables I am going to say dot. Data for developing this training model will be training. Method that we are going to use is called KNN. Let's use a tune length of 20. And for TR control, we'll use this TR control that we have created. And another thing that we must use is pre-processing of the data. If you look at first few values of the data using head, you will notice that the GRE values are in hundreds, so 380, 660, 800 and so on. And GPA values are quite low. So in order to create a level playing field, we need to normalize this data. So to standardize the data, I'm going to subtract mean from each value and then divide it by standard deviation. So we can achieve that very easily in Caret by doing PRE and then capital PROC. And we can specify that we are going to use center, which is the mean, and scale, which will be standard deviation. So let's look at what do we have within fit. So it indicates that the method used is k nearest neighbor and number of samples is 284. Then there are three predictors, GRE, GPA and rank. And we have two classes that we created. No means student was not admitted and yes means student was admitted. We have carried out a 10-fold cross validation repeated 3 times. So in each cross validation, training data is split into 10 parts or 10 folds, and 9 of them are used for creating the model and the remaining one is used for assessing the model. So you can see model accuracy and kappa values have been assessed and they are listed here for various values of k. And finally it says that the accuracy value was used to select the optimal model, and that value we get when k equals 33. We can also plot FIT fit. So it shows us for various values of k what are the accuracy value obtained, and you can see somewhere here we have the highest value, so this one is for 33. We can also look at variable importance. So out of 3 values, the importance values are spread between 0 and 100, and you can see that GPA turns out to be the most important and GRE turns out to be the least important. So to further assess the model, let's look at prediction using predict function. So the model is fit and new data that we are going to use is test data. Let's store this in PRED. In fact, if you run PRED, you'll see that it has predictions like no or yes. So now we can create confusion matrix using PRED and our test data $admit. You can see that in the test data 79 students were actually not admitted, and the prediction based on the model also says they should not be admitted. So that's a correct prediction. Similarly, there were 4 students who were actually admitted and model also predicts they should be admitted. So 79 plus 4 is 83 out of total of 116.7155. So that's the accuracy value that you see here. We also have 95% confidence interval, goes from 62% to 79%. No information rate. So basically if all students are rejected, the model would have been correct about 70.69% of the time. So model performance obviously has to be better than that, and in fact we are better, but there is a scope for further improvement. In this case we used accuracy to select the optimal model, which gave us k equals 33, but we can also use ROC. Now we can make few changes to use some other method instead of accuracy. So I'm going to add a line in TR control class probabilities, let's say true, and we can also say summary function is to class summary. So note that class probabilities are needed if we want to use ROC for selecting optimal k. So another thing that I want to do while developing the model is, let's say metric equals ROC. So default value is accuracy, but if we want to use ROC, we have to say that the metric should be ROC. Another thing we can do is you can make use of tune grid. We can say expand.grid k equals 1 to, let's say, 60. So let's rerun train control. So I'm going to take this out, just the bracket. So let's run this. We can keep set.seed same, and then we can run the fit line. So next we run fit, and you can see that now ROC is used for optimal k. Best ROC value we get is for k equals 32. So basically this is area under the curve, which is 0.671. We can plot fit. So for higher values of k, we get better ROC values. Let's look at variable importance. So more or less same, and let's do prediction, confusion matrix. We do get better result by using area under the curve using ROC. So earlier our accuracy was about 71%, now it is more than 73%. Another thing you may notice is that more data points are for no and less data points are for yes, where students were actually admitted. So if we handle this class imbalance, we may be able to further improve accuracy. We are going to use Boston housing data for regression, where y variable is numeric. There is a data set called Boston housing within ML bench package. So let's change name to data, which is a shorter name. So you can see there are 14 variables and 506 observations, and the dependent variable of interest is MEDV. You can say question mark Boston housing, and you can see each variable is explained. MEDV is median value of owner occupied home in thousands of dollars. So for data partition, I'm going to use the same process that we used earlier. So I'm going to copy and paste. So let's use a TR control, and then we can use train control. So if you run fit, so it says that we have run k nearest neighbor method with 355 samples, and there are 13 independent variables or predictors. And again, this is cross validation with 10-fold and 3 repeats. And then it gives us root mean square, R squared values, and MAE, mean absolute error, for various values of k. And towards the end it says root mean square error was used for selecting optimal model based on which k is equal to 2. Let's plot fit. You can see that we get lower values for root mean square error, which is better when k values are low, and after that it continues to increase. So it shows us that LSTAT, that's the most important variable, followed by RM, indus, and so on, whereas CHAS, that seems to be the least important variable in this data set. We can also do prediction and save results in PRED. So predict using fit model, and new data is test. So note that for regression our y variable is numeric. So now we calculate the root mean square error for assessment using predicted values PRED and test $MEDV. So it comes to about 6.15. So we have actual values on x-axis and predicted values on the y-axis. So you can see how is the performance of the model. Obviously this is not a perfect prediction. There is a scope for improvement. Now another thing we can do is we can specify that instead of the default root mean square metric, so let's choose R square and then rerun the model, and you can look at the plot. Obviously R square is higher the better type of characteristic, so we get the highest value for R square at k equals 2. We can also see what happens to predictions. So 6.15, not much change actually, and you can see actual versus predicted values. So we don't see any major improvement based on this scatter plot.